All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? Good to hear. We're end of week 4 already, and so this is we're basically a quarter done through the semester. So it still kind of feels like we started yesterday, but I know probably for a lot of you guys, midterms are coming up, and things are going to get busy really soon. Okay, and so the topic for today is going to be boundary conditions, right? And so on Monday, what we did was we covered kind of just the basics of meshing, right? And so hopefully after our lecture Monday, you'll have a better understanding of kind of why we made certain decisions and why we set things up a certain way for the meshing. Okay. Today it's going to be boundary conditions turn. And so, boundary conditions is another thing that we've been doing. But it's also one of those things where, we've kind of just been doing what the instructions say. So, hopefully after today, you'll have a better understanding of, what boundary conditions are, why we need them, and, what purpose they serve for finite elements. Okay, so I don't think I have any announcements, not that I can think of. I am starting to think about your guys' midterm project. Okay, and so remember, so in this class we don't have any exams, but there is going to be a midterm project, and so I'm hoping I am starting to think about it. So I'm hoping to get that to you guys sometime next week, and then it'll be due probably 3 or 4 weeks after that. So you'll have a pretty decent amount of time to do it. Okay, at least that's my goal. Okay, so any questions on anything before we get started? Yeah.
Do you have any solid details about what the project entails?
Yeah, so the project is
the like the same as the final project for 410?
No, so it's going to be different. And so the so for 410, for those of you who weren't in that class, I basically let the students kind of pick, something that they wanted to analyze with finite elements. And so for this class, I do want to constrain it a little bit more. And so I'm going to pick kind of what the subject is. I'm thinking about giving you guys some options. And so it's just so that not everyone has to do the same thing. And so I'm hoping to have maybe 2 or 3 or 4 different options for you to do. And I want you to perform basically a finite element analysis on that. And so you can almost think of it as like an activity plus. And so, for the activities, the kind of the purpose of the Ansys activities is to kind of introduce new features of Ansys to you and kind of walk you through kind of the process of doing that. For the project, it's I kind of want to step back and kind of take the training wheels off a little bit. And so what I imagine is, I'm going to give you a geometry, I'm going to give you a situation, and I'm going to say that, this is these are the informations that we want to obtain from this finite elements. And I want you guys to basically set up the finite elements in a way such that you can obtain that result in an accurate and efficient way. Okay. And since this class is technically, the name of the class is Computer Applications and Engineering Design, I'm thinking there's going to be a design aspect to it too. And so what I'm thinking is, I'm going to give you guys a geometry, and then I want you to perform finite elements. And then based on your finite element results, I want you to suggest the design improvement and then test that design improvement virtually as well. Okay. And then you're going to write it up into a report that makes it, that presents it in a professional way. Okay. So that's what I'm thinking right now. But, I'm going to kind of form the idea a little bit more firmly by next week. And then hopefully by next week, you'll have the specs and the geometry so you can get started with it. Okay. I wanted to time it so that I give you the project after the third Ansys activity, because I think after the third activity, you've kind of reached after the third activity, you guys will have reached a state where like you're fairly competent in Ansys, I would say. Just because, by that time we'll cover all the really kind of basic features of Ansys. And so after the third activity, you should be good to go to at least start working on a project like that. Okay. Okay, so are there any other questions before we get started? Okay, all right, so let's go ahead and start talking about boundary conditions. All right, and so similar to meshing, boundary conditions are also a really important part to finite elements. But there's a lot less to talk about boundary conditions than meshing. And so, today is probably I'd say probably the only time this semester where we're going to dedicate a whole day talking about boundary conditions. But it's something that you're going to have to set for every finite element simulation that you have to do. Okay. Okay. And so strictly speaking, boundary conditions hopefully is a term that you're familiar with, outside of finite elements, right? And so it's not just a finite element thing, it's actually a math thing, right? And so what boundary conditions do is that they describe, how a solution behaves on the boundaries of your domain. Okay? And like I just mentioned, boundary conditions are needed for any differential equation, right? And so, it just so happens that finite elements is a computational way to solve differential equations. But even if you're solving them by hand, or if you're solving differential equations using a different method, like finite difference or finite volumes, right? You're going to need boundary conditions in some way, shape, or form, okay? Right. And so the way I'll describe it is, they're always going to be needed to specify a complete solution. Okay. And so let me do a 1D example. Okay. So hopefully an example that maybe specifically shouldn't look too familiar, but the methods that we're going to use are going to be familiar. Okay. And so let's take a ordinary differential equation. Okay. And so our differential equation is going to be d squared u dx squared is equal to 3x squared. Okay. And so in this equation right here, what I want you to do is I want you to solve this differential equation for the function u. Okay. Okay. And u is going to be a function of x. Okay. And so a fairly simple equation, right? And so differential equations, there's lots of different ways that you can solve them. But I gave an intentionally easy one here just so that we can do it very quickly. Because when you're given kind of just the straight derivative like this, and there's no extra terms to it, you can just solve this just by straight up integrating. Okay, and so let's go ahead and integrate this. Okay, so we'll apply an integral on both sides. Notice that these are indefinite integrals, and so we don't have any bounds on these integrals. Okay, so that's going to be really important. And our integration variable is going to be x. So we're going to need to add our dx on both sides. Okay. And so on the left-hand side, after we integrate once, one of the orders of the derivatives are going to go away. Okay, so we're going to end up with du dx. Okay. And on the right-hand side, we're going to integrate once, and so this is going to be x cubed, right? Because the integral of 3x squared is, we do kind of the reverse, what do you even call it? Reverse power rule, right? And so that's you divide by 3 and you add the 3 to the exponent. Okay. And since we were performing indefinite integrals, we have to add this arbitrary constant, right? And so just a reminder, this C1, arbitrary constant. Because remember, when we're integrating and we're not specifying the bounds for the integration, our solution is only valid up to an arbitrary constant. Okay. All right. And so we're almost there. And so since we have du dx, we can go ahead and integrate one more time. Okay. And dx. Okay. We integrate one more time, and then we'll have u of x, okay, is equal to integral of x cubed is going to be 1/4 x to the 4th plus c1x plus another arbitrary constant c2. Okay. And so this right here, this is our general solution to the differential equation. Okay. It's the general solution because it's we haven't completely solved it yet. Okay. Because in order to get a complete solution to this differential equation, we have to specify values for our arbitrary constants, right? C1 and C2. And the only way that we can do that is we apply some boundary conditions. Okay. All right, so on the next page, we're going to specify their values by applying a couple boundary conditions. Okay, any questions on this so far? Okay. All right, so let's go ahead and start applying some boundary conditions. Okay, and so since we have two arbitrary constants, we need to apply two boundary conditions. And so these I'm just going to specify arbitrarily. And so let's say that we have one boundary condition at x equal to 0. Okay. And so I say that u of 0 is equal to 18. Okay. And then the other boundary condition that we'll have is, let's put a boundary condition on the derivative. Okay. And so let's say that du dx at x is equal to 10. This is going to be equal to -5. Okay. All right. And so we're going to specify both of these boundary conditions in order to solve for C1 and C2. Okay, so let's start with the first one. Okay. And so in this first boundary condition, we're going to plug in 0 for x into our solution u of x. Okay. And so we're going to evaluate u of 0. Okay. It's going to be equal to 1/4 0 to the 4th power plus C1 times 0 plus C2. Okay. And this is going to be equal to 18. Okay. Okay. And since those first two terms have a 0 multiplying by them, they're going to equal 0. Okay. And so applying our first boundary condition, we get simply C2 is equal to 18. All right. And so to apply our second boundary condition here, we have to take a derivative. And so let's take du dx. Okay. And so we do that, we end up with x cubed plus C1. Okay. All right, so now let's evaluate this boundary condition at, or let's evaluate this derivative at x is equal to 10. Okay, and then we're going to set it equal to -1. All right, so du dx evaluate at x is equal to 10. This is equal to 10 cubed plus C1 is going to equal to -5. Okay. We can solve for C1 from this. And we get that C1 is going to be equal to -1005. All right, and so now that we solve for our two constants here, we can go ahead and plug that into our general solution, and that's going to give us our complete solution. Right? And so our complete solution, u of x, is going to be equal to 1/4 x to the 4th minus 1005x plus 18. And so this right here is our complete solution. All right, and so that's kind of a simple 1D case of kind of showing you why we need boundary conditions for, to solve any kind of differential equation. Okay. All right, any questions on this? Okay. All right, and so, finite elements is exactly the same way, right? Because remember, finite elements, end of the day, what you're solving is you're solving a differential equation, right? You're not using an analytical method like this. you're going to be using computer methods, but it still has the same requirements, right? And so in order to get a complete and fully specified finite element solution, you need to apply the boundary conditions. Okay. And so since FEM is solving differential equations, you also need boundary conditions. All right. The nice thing about using about applying boundary conditions in FEM is that oftentimes your boundary conditions are going to take some kind of physical form, or it's going to have some kind of physical intuition. Okay. And so, think about the boundary conditions you've applied in the last two activities, right? And so we've applied a boundary condition like a fixed support, right? And so fixed support, you can kind of visually see what's happening, right? And so you're taking your geometry and you're fixing it at a certain location, right? The other type of boundary condition that we've applied are loads, right? So forces and pressures, and that's very easy to kind of visualize what's going on, right? So you're applying some kind of external load onto your geometry, and that manifests itself as a boundary condition, right? And so even though they kind of take a physical form for finite elements, they serve the exact same need as what we just did for the previous example, whereas it allows you to find a complete solution to the differential equation. Okay. It's just that for finite elements, it becomes a little bit nicer. Okay. All right. And so kind of before we kind of get a little bit more into types of boundary conditions, I want to kind of give you guys my what I think of boundary conditions or what their role serves for finite elements. Okay. And so to me, when I apply boundary conditions, these are kind of like the inputs or the instigators for your finite element solution. Okay. Okay. And so boundary conditions are the actual thing that makes your physical system do something interesting. Okay. And so that's what I mean when I say inputs or instigators. Right? Okay. And so, when you think about, a physical system, and so let's take this dock cam right here. Okay. And so by itself, this dock cam right here, I guess you can't really see it on Zoom, but it's just a projector thing, right? And so by itself right here, it's not really doing anything interesting, right? It's just kind of chilling on this table, right? But right now, as it's kind of sitting here, its behavior is being governed by, the equations for static structural, right? And so right now it's obeying all the laws for static structural, right? But as you can see, even though it's obeying the equations for static structural, it's not really doing anything interesting, right? It's just sitting here. It's not until I take my hand and I kind of gently push this down so I don't get in trouble, right? That's when the dock cam actually starts to do something interesting, right? And the act of me kind of applying an external load and making it do something interesting, that's what boundary conditions essentially do. Okay. All right. And so the way I want you guys to think about it is, when you have a physical system, okay, of course you're going to describe things like the governing equations and the material properties. Okay. And so the governing equations and material properties, these two things kind of serve, they're obviously, different things, but they kind of serve the same purpose in terms of, how they affect your finite element solution. Okay? And that these are basically, these kind of set the rules for how how the system is going to respond. Okay. And so, these basically determine or describe how the system will react. Okay. And so the material properties, governing equations, what they basically say is that if you expose your system to some kind of external stimuli, then those things tell you, how much it's going to deform, how it's going to deform, what kind of shear stresses there are going to be. Okay. Whereas the boundary conditions, these things are actually the external stimuli. Right? And so in other words, one way that you can think about it is that your physical system, through its governing equations and through its material properties, are reacting to what the boundary conditions are causing to it. Okay. Okay. Any questions on any of these? Okay. All right. And so without boundary conditions, like you actually can't even run a simulation, right? So nothing interesting can happen. And Ansys will actually stop you, right? And so some of you have actually tried this already. And so when you actually try to run a simulation in Ansys without boundary conditions, Ansys will tell you that it doesn't have enough boundary conditions to solve for a solution. Okay. It will actually give you an error that basically says that nothing's going to happen. Okay. And so the bare minimum of boundary conditions that you need to apply before you can run something in Ansys is you need to have at least one constraint type boundary condition. Okay. You need one of those for sure. And so there's no negotiating that. And most of the time, or I would say often, you also need one load type boundary condition. Okay. Okay. not always. And so, we'll talk about ways of, how you can run a simulation without a load. But at the very least, you need at least one constraint type and at least one load type. Okay. And so what we're going to do next is I'm going to go over, the two different types of boundary conditions. Okay. And so there are constraint type boundary conditions and loads. And so I'll describe what those are, and what effects that they have on the solution. Okay. All right. So let's start with the constraint type boundary conditions. Okay. So these have a fancy mathematical name, and so the fancy mathematical name for these are called Dirichlet boundary conditions. And so it's only recently that I started using the terms constraint type and load type, and so sometimes I might accidentally say Dirichlet boundary conditions, and then the other type of boundary condition is called Neumann, just because that's just how I learned it, initially, but I think constraint type and load type are a little bit more intuitive to at least what they do for this for the solution. Okay. All right, and so constraint type boundary conditions, the way that these work is that they force the primary solution variable to have a certain value on the boundary, on the indicated boundary. Okay. Okay. Or in other words, what you can say is we're constraining the values of the solution to be, to have a certain value. Okay. All right. So an example of this that we've been using quite a bit is the fixed support. And so with the fixed support, what you're specifying or what you're requiring is that you're requiring the displacements or the deformations to be zero. Okay. And remember, when you're running a static structural simulation or any kind of linear elastic simulation, the primary solution variable is your displacement. Remember, the primary solution variable is the quantity that Ansys or any kind of finite element software, that's the first thing that's going to solve for, right? And so you solve a static structural simulation. The first thing that's going to solve for is, what's the deformation, what's the displacement in this part, and then from there it'll compute things like your strain and your stress and your normal stresses and things like that. Okay? And so a constraint type boundary condition will place, will force a value on the primary solution variable. And so, for thermal simulations, remember the primary solution variable is the temperature. And then for fluid simulations, the primary solution variable is the velocity. Okay. And so, it's always good to be aware of, what your primary solution variable is, just so that what your constraint type boundary conditions are going to be. Okay. Okay. Any questions on this? Okay. So let's relate this to the first example that we did today. Okay. In our 1D example, in our 1D example, we did have a constraint boundary condition. Okay. And our constraint type boundary condition for our 1D example was the condition at x is equal to 0. Okay. Right. Because look at what we're doing here, right? And so in our 1D example, our primary solution variable was u, right? And so by forcing u to have a value of 18 at the origin, then that's the same thing as a constraint, okay? And so when we say that u of 0 is equal to 18, what we're saying is this is a constraint type boundary condition, okay? All right. Okay, so remember what I just mentioned on the previous page, that whenever you run a finite elements, you always need at least one constraint type boundary condition, right? And you can come up with a very simple kind of physical reason why, at least for physical cases, or at least for structural cases, okay? Okay. And the reason it's needed for structural simulations is that if you don't have a proper constraint, then what you're going to have is rigid body motion, okay? And oftentimes you don't want that. And because remember, when you're doing a static structural simulation, you want your structure to be static, right? You don't want it to start moving everywhere. Okay? And so let's just kind of show you just a quick example of what happens when you don't have one. Okay. And so let's say that we have a beam, but this beam is not bolted down. And so let's say that we have rollers on both sides. Okay. And so if we apply a force on this beam going this way, right, then as we can see here, the beam is going to start to move. Okay. It's going to be making its way downtown, rolling fast. I forgot the next line, but it's okay. And so basically, instead of a beam, what you have here is a skateboard instead. Okay. Which is not good because you don't, unless you're doing a dynamic simulation, you often don't want your beam to be rolling like that. All right. So mathematically, what purpose does constraints serve, right? And so mathematically, what your constraint type boundary conditions serve is that they give you a reference point from which all your other solutions can be measured relative to. Okay. Because without that reference point, there could be basically an arbitrary constant that you can add to your solution and have it still be valid. Okay. And so think back to our 1D example, right? And so when we applied our constraint type boundary condition, what that basically gave us was a value for C2. And C2 was our basic constant addition, right? And so if we change C2 to anything else, that's going to shift our solution up or down, depending on our value for C2, right? And so C2 here, is kind of like our reference point from which all the rest of the, solutions depart from, okay? Right, and so if you actually try to solve that first equation without your constraint type boundary conditions, you'll find very quickly that it's impossible, right? Or I should say it's impossible to specify a value for C2 without a constraint type boundary condition. Okay. And so you can actually try it for yourself. And so if you go back to our general solution for our first example, and you try to solve it using two derivative type boundary conditions, right? And so instead of saying u of 0 is equal to 18, maybe change that boundary condition to du dx at x is equal to 0 is equal to 5 or something like that, right? And you'll find very quickly that you're not able to solve for C2, and your solution will just be arbitrary up to that constant, okay? And so in the lecture notes, I actually do this, but just because I want to make sure I get through everything, I'll leave that for you guys to try out on your own. Okay. Okay. Any questions on this? Okay. All right. And so other forms the constraint type boundary condition can take are displacement types. Okay. Right, so we're not just limited to fixed support. And so fixed support is something we'll use often just because it's really convenient. But there's other ones out there. Okay. Displacement type boundary conditions are really useful for when you want to apply things like a roller. Okay. Because when you apply a fixed support, what you're basically saying is that all components of displacement x, y, and z are going to be 0, as well as the rotation, right? And so those parts can't rotate. But if you only want to make it so that I only want to constrain maybe the x and y components of displacement here, then you can apply a displacement type of constraint, or you can say that two of my displacement components will be 0, but the other one will be free. Okay, so that's another common one. Okay. And again, for thermal simulations, the constraint type boundary condition will be temperature, right? And so when you specify that the temperature of a certain object or certain surface on your model is a specified temperature, that's placing constraint on the temperature. Okay? And then for fluid simulations for CFD, your constraint type boundary conditions will be like velocity or flow. And so this concept of constraints, even though the term constraint, I think has a much more structural flavor to it. But the same concept will apply to your thermal simulations and your CFD as well. Okay. Okay. And so those are the constraint type boundary conditions. So now let's start talking about the load types. Okay. And so the mathematical term for these types of boundary conditions are called Neumann boundary conditions, which again is not that important. It's just the name. But you might hear me slip up and call them Neumann boundary conditions at some point. And so when I say Neumann, what I mean is load type. Okay. All right. And so the way I define load type boundary conditions is that these kind of encompass everything else. And so all the other types of boundary conditions that you see in Ansys, they are load type boundary conditions to some degree. Okay. right? And so basically any type of boundary condition where you're not directly specifying the primary solution variables, I would classify those as load type boundary conditions or Neumanns, okay? And so explicitly or mathematically, the way that these boundary conditions take form is that they involve some kind of derivative of the primary solution. Okay? Okay. Right. Sometimes it is as simple as saying that, the derivative of your solution is going to be this on this part of the domain, but oftentimes it takes some kind of complex form. But some way and somehow, the derivative is in there, at least one way or the other. Okay. All right, and so in our first example, we had kind of a pure, I call it like a pure Neumann boundary condition, where we specified that the derivative of the solution at a certain location had to be a certain value. Okay. And so in our 1D example, the boundary condition du dx at x is equal to 10 is equal to -5. Okay, this was our load type boundary condition. Okay, because again, it involved the derivative, and it didn't directly specify the value for u. What you're doing instead, you're specifying the derivative of u. Okay, you can almost call these boundary conditions, and I hesitate to use this term, but it's kind of makes sense from a mathematical perspective. These are kind of more weakly enforced boundary conditions, right? And so what I mean by that, it doesn't have a direct influence on the value of u over there, but it more kind of has an indirect influence, right? And so by specifying that the derivative has to be this, then kind of indirectly you're specifying that the solution has to reach a certain value at those locations. Okay. Any questions on this? Okay. Okay, and so some common types of load type boundary conditions that we've seen so far are things like the force and things like the pressure. Okay. Right. So these are kind of the most basic kind of load type boundary conditions that we can apply. Okay. But probably you guys have seen when you go to apply these boundary conditions that there's a lot of other types there as well. Okay, but all of those other types of boundary conditions are kind of spin-offs of a force or a pressure. It's just they're kind of more specialized for certain situations. Okay? Right, and so some kind of so some examples from thermal and for fluids, and so an example of a load type boundary conditions for a thermal simulation would things be like heat flux. Okay. Another example would be like convection. Okay. That's a very common one. And then one more, let's say radiation. Okay. Radiation is also kind of like a load type boundary condition because it doesn't directly specify what the temperature is going to be. Okay. Right. And so some examples of the load type boundary conditions in fluids would be things like the pressure. Pressure, I think, is the most common one, but you can also apply things like the shear stress. Or normal stress. Okay. Normal stress is almost like pressure. It's almost the same thing. Actually, you guys know what forces and pressures are. Okay. And so strictly speaking, even though, we think of these kind of load type boundary conditions as, these are kind of the main instigators for interesting action in your finite element simulation, right? And so if we go to the doc cam from earlier, right? When I karate chop it, that's providing a force, right? I'm not directly saying that the displacement has to be a certain way. What I'm doing is I'm applying a force onto this guy, okay? But strictly speaking, load type boundary conditions are not actually required. Okay? And so you can get a full finite element simulation just from constraint type boundary conditions. Okay. And so, just as an example, right? If we go back to our, our very first, our very first 1D example, right? If we change the second boundary condition to a constraint type, right? So let's say that instead of the derivative of u at x is equal to 10, let's say that we just directly specify that we say that u at x equals 10, this has to equal 500. Okay. Right. And so we basically eliminate the load type boundary condition. We only have the constraint. We only have constraints now. What you'll find is that you can solve it just fine, right? The opposite was not true, right? And so, and unfortunately, that was the one I kind of skipped. But if you try to solve that 1D equation with two derivative boundary conditions on both ends, then you wouldn't be able to solve it. But you can with constraints. Okay. And so, kind of a more physical example, just to kind of prove to you that it's possible. Let's take our beam from earlier. Okay, but let's actually fix it this time. Okay, so it's not making its way downtown. Okay. So let's say that we're fixing the beam right there, and we're going to have a roller on this end. Okay. By placing the fixed support here, or a pin support here on the left side, what we're saying is that this is our fixed support or fixed constraint. Okay. And so that's one constraint type boundary condition. Okay. If on the other side, let's say that we say that the displacement of this end right here has to be a certain amount. Okay, so let's just say it's 5 centimeters, just completely arbitrarily. Okay. And so we place a constraint such that the displacement over there has to be 5, right? You'll be able to solve this equation, right? And so what you're going to have is, you're going to have a distribution of stress inside this beam. Okay, it's going to look a certain way, and then the deformation is going to be 5 at that end, and it's going to decrease as you go to the other end. Okay. And so this is a perfectly valid simulation that's not gonna roll away from you. It's not going to do any weird stuff. It's perfectly valid, and we did all this without any load type boundary condition. Okay. But with that said, when we're, because we're using finite elements from, a purely practical standpoint, right? And so since we're using finite elements to model, physical engineering systems, 99% of the time, you're going to have some kind of load, because that's often what you're going to be interested in looking at, right? Because you have some kind of external force, external pressure that's going to be on your structure, and you want to see how it deforms, right? So 99% of the time you are going to have a load, but strictly speaking, it's not actually required. And so, but this part of this piece of information here is kind of more trivia for you. But but if you do run into that 1% of situations where you're not actually applying an external load, just know that you can do it and it'll be just fine. Okay. Any questions on these? Question. All right, so the stress will be coming from the weight of the beam, or would it be the weight, or would it be the force? Oh, that's a good question. And so, in this situation here, we're kind of forcing the beam to deform. And so because of that, there's going to be internal stresses within the beam that want to basically return the beam to its resting configuration, right? And so if you take like a pen, right, and you forcibly stretch it, right? Even though you are applying a force to stretch it, another way that you can describe is, I'm forcing the tip of this pen to displace like, maybe a centimeter, okay? There's going to be some internal stresses that develop within that pen that want to bring it back to its resting configuration, right? And so, applying a displacement is kind of almost, you're kind of applying a load, but you're kind of doing it in a different way. Yes, yeah, and of course it's depends on the material properties. Yeah. Mm-hmm. Okay, and so those are the two types of boundary conditions that we have available to us in Ansys. Okay, and so now let's start talking about some practical considerations of how do you actually choose what boundary conditions to apply. Okay. And so the number one, the number one most important thing for applying boundary conditions is that they have to be physically consistent or physically accurate to the situation that you're trying to model. Okay. Because remember, the reason that we run finite element simulations as engineers is that we want to replicate a real life situation, right? And so we have a real life kind of structure or real life kind of thermal situation, and we want to find out, what's going to happen to this structure or this thermal situation when we expose it to certain loads. Okay, and so in order to get an accurate result, your boundary conditions have to be accurate to whatever physical situation that you want to model. Okay. Which when you kind of say it like that, it's kind of obvious, but I think you'd be surprised at some the things that that not even just people, things that that you would do, that I would do, just to get a simulation to work, right? And so sometimes sometimes you kind of get a little bit frustrated with the software when it's not working with your type of boundary conditions, and so you try to change things up, okay? And you might get a result, but that result might not be physically consistent. Okay? And so this is something that you always kind of have to remember, that your boundary conditions, they have to represent reality. Okay. All right. So sometimes this is really easy. And so sometimes it's really easy to say that from this structure, I know it's going to be bolted to the wall here, and so that tells me right away this is going to be a fixed support. Okay. Okay. Right. Sometimes you look and and this gets easier, as you run more and more finite element simulations of, here's the physical situation, here's the physical external stimuli. I know how that will translate to a boundary condition, right away. Okay. But sometimes it's not going to be obvious. Okay. And so, just a simple situation I thought off the top of my head. So, let's say that you're doing a finite element simulation of the Golden Gate Bridge, okay? And then one of the important forces that you need to consider are pedestrians that are walking across the bridge, right? And so, across the bridge, you're going to have a variable number of pedestrians, and they're going to be applying force in a variable number of ways, right? And so sometimes you might have more pedestrians on one side of the bridge or the other one. Sometimes they might be all clumped up together. Sometimes they might be spread out, right? And even when they're spread out, they're going to be applying force directly through their feet, right? And so it's not going to be like a flat thing. And so, should you apply the force as a distributed pressure force, or should you apply the force as individual point forces where each individual person is? Or should you apply it as like pressures, on the outlines of all their feet? It's not clear, right? It's not an obvious thing. And so in those situations, you kind of have to try to fit a round peg into a square hole a little bit, because the options in Ansys are not, they're not going to give you an option for like, 100 people standing on a bridge, right? And so they're only going to give you the basic pressure, they're going to give you the basic force, right? And so sometimes you have to make a little bit of an assumption of, let's take this force and let's, just put it in a way that makes it easier for finite elements. But, there's kind of an art to it too, okay? And so kind of the takeaway from this statement here is that, you want to be as physically realistic as possible, especially in terms of like the values of like the force, or the displacement you're working with. But exactly how you do it and kind of the fine details of like, where you apply it, what values that you do, those, you kind of have to use your best judgment sometimes, okay? And sometimes that's not easy. And sometimes it takes some iteration to try to get it exactly right, okay? All right. And so I'd say this is kind of the most important thing for boundary conditions is to always remember that, they're there. The reason they're there is to represent a physical situation, right? Which seems obvious, but, but I would say most of the mistakes that I see people make with boundary conditions is that they kind of forget this. They kind of forget this point, okay? Okay. And so, those mistakes that I see is that either people pick the wrong boundary condition. So maybe, a different type of boundary condition would represent what they're going for a little bit better. Or they just don't account for something, right? So sometimes, there's a certain phenomenon or a certain kind of external stimulus or external load that's actually being applied on your structure, but that's not being accounted for in the boundary conditions, okay? And so you have to be really explicit here and think about, every single load that your structure is experiencing, and then make sure that you and kind of incorporate that into a boundary condition in some way. Okay. Never assume anything. Right? So always assume that, if it's something present in the real life, you have to explicitly put it in as a boundary condition. Otherwise it's not going to be there. Okay. Okay. Okay, and so the other practical consideration that I have here is that, think about the location and how you're applying the boundary condition. Okay, and so when you're doing kind of a general 3D simulation, your boundary conditions can be applied either at a point, it can be applied on an edge or on a surface. Okay? right? And so what you end up choosing, of course, depends on the nature of the boundary conditions, or depends on the nature of the physical situation that you're trying to model, okay? But generally, you want to apply boundary conditions on the largest entity possible, okay? And so for 3D simulations, that means surfaces, right? And so generally, if you can, and sometimes it doesn't make sense, and I get it, but for 3D simulations, if you can form your boundary conditions in a way such that you're applying it on a surface or a face, that's usually going to lead to the highest quality and the best the best solution. Okay. Okay. Right. And the reason for that is kind of has to do with stability. Okay. Because if you apply, let's compare, applying a force at a point versus applying a force at a surface, right? And so if you apply a force at a point, right, and so you can use kind of your own back as kind of an example, right? Let's say that someone wants to take a point force, and so they're going to take their finger and then stick it into like a discrete point on your back, right? And so that's going to feel a lot different than if they took that same amount of force, but they distributed all throughout your back, right? And so sometimes you do want to apply that point force because maybe you are modeling someone just being an annoying prick and just poking you in the back, right? But if it's a force that you can actually distribute across the surface, and that makes sense, then that's something that's going to be more preferable, and that's going to give you a generally a higher quality finite element solution. Okay, any questions on this? Okay, all right. And so one note that I'll make for that is that even though we've been discussing how important boundary conditions are, you don't actually need to apply boundary condition on every single surface. Okay? And so far we haven't, right? And so you think back to our last two activities, there are a bunch of surfaces and a bunch of edges in our domains where we didn't apply any boundary conditions. Okay. And so technically you do need a boundary condition on every surface, but when you don't apply a boundary condition there, what Ansys is going to do is that it's going to apply a default boundary condition. Okay? Okay. And that default boundary condition, of course, it depends on the equations that you're solving. But for a structural simulation, the default boundary condition is going to be stress-free. Okay. And so all the stress-free boundary condition means is that there's going to be no external constraint or no external load being applied there. Okay. Which seems like nothing, right? And so this is basically the do nothing boundary condition, right? It seems kind of superfluous here, but mathematically applying a stress-free boundary condition actually does something to the solution. But just know that Ansys will do that by default. And so don't feel like you have to go into your Ansys models and say I need a boundary condition on every single one, because if you don't do anything, then Ansys will apply that. Okay. But also keep in mind that if you don't want a surface to be stress-free, right? maybe it is leaning against something, or maybe there's going to be some kind of, load there, then make sure you specify that, right? And so remember, don't assume anything, right? And so if you don't want a surface to be stress-free, then make sure you specify that in your boundary conditions, okay? Okay. And so one last point that I'll make is that, it is possible to apply multiple boundary conditions at the same location. Okay. Oh, forgot the most important word, multiple boundary conditions. Okay. And so it is possible, right? And so don't feel like, when you're doing your Ansys simulation that you apply one boundary condition here and then that's it, okay? And so sometimes this makes sense because sometimes a particular surface will be subjected to, multiple loads at the same time, right? And so one example that's out there is, maybe you're applying a wind load on a bridge, right? So maybe you're applying wind on a certain surface, but there's also going to be a load from, maybe cars riding over the bridge as well. Okay, and so you have kind of both the wind and the car loads applying a load at the same time. Or even for a thermal case, right? And so for a thermal case, you might have an example where you have a surface and it's being cooled by convection as well as radiation at the same time. Okay, and so it's possible to have multiple loads. What's not possible is that if you try to apply a constraint and a load at the same time, the constraint is going to win. Okay. Okay. And so, it'll almost be like the load just wasn't even there. Okay. Because what's happening is that, let's say that you're applying a load on a surface, but if that surface is fixed, right? Then that load is not going to transmit to the rest of your solid. It's just going to hit that fixed support and then just kind of dissipate. Okay. And so I'll do a very simple example with a beam on the next page, and then we'll call it a day. Okay. But before I do that, are there any questions on this? Okay, and so let's see what happens when you try to do exactly this with the beam. Okay. And so we'll use our skateboard beam from before. Okay. So let's say that we have a beam like this. Right, and so on one side you have a pin support, another side you have a roller. Okay. If you try to apply a force, if you want to displace this beam, you would apply a force on the right side or a horizontal force on the right side, because that's where the roller is. But if you try to apply a force right here, okay, on the side where it's pinned to the ground, nothing's going to happen, right? So there's no way for that force to transmit to the rest of the beam because it's just hitting that fixed support. Okay. And so here, what you have is you have both a load and a fixed support here at the same time. Okay. But when you do this, it's almost as if the load is not being applied because there's no way for it to actually deform the structure because it's just, hitting up against that constraint. Right, and so if you actually wanted to get some kind of deformation on this beam, you would apply this force on the other side, right? Because that other side is free to deform because it has the roller, okay? And then that deformation is gonna propagate to the rest of the beam. Okay? But if you try to apply a force in a direction where the structure is already fixed and it can't deform, then it's not gonna do anything. Okay? And so just kind of remember that constraints are always going to override your loads in situations like this. So this, I will say this is not very common. And so, if you're modeling a real life situation, most of the time, you're going to avoid situations like this because it's, a lot of times you're not going to have loads that are being applied directly at the same part as your constraint. But just kind of be aware of this. All right. Any final questions before we wrap it up for today? Okay. All right. So that's all I got planned for today. So thank you guys for tuning in. On Monday, we're going to talk about material properties, which I think is the last of the trio of kind of the basics of finite elements. And then next Wednesday, we're going to do our next activity. Okay. So hope everyone has a good weekend. Enjoy the rest of your evening, and I'll see you guys on Monday. Thanks, Raphael. Have a good weekend.
Activities due Friday night, right?
Friday night, correct. Yeah. Sure.
After the last problem, like frame.
Yeah.
Do we assume that has a factor of safety too when we're
Yes.
considering the
Yeah.
issue?
You can assume it's the same factor.
Okay. Thank you.
Yeah.
Yeah, or cardio questions. I like that. Yeah, no,
It's nice to see that you're talking about the Dirichlet and Neumann conditions because we did that in 538 throughout like the whole class.
Oh, really?
And to like finally get a physical representation of everything.
Nice, nice.
Because all we did is like manipulate the heat equation in all different kind of ways, like separation of variables, like eigenvalue expansion, all these things. And I'm like, why are we doing all this? So it's finally nice to see some connection to those boundaries.
That's good. That's good. Who taught you 538? Was it Dr. Weiss?
Yeah.
Okay. Okay, that's good that you use the same terminology because it's
Yeah.
yeah, other people use different stuff, but this is how I've always been taught.
Probably one of the most challenging classes.
Yeah, PDEs are always going to be a hard subject. They make you guys take that one, right? Either that one or 438.
Yeah, it's a must. Yeah.
See you guys. Have a good weekend.
I'm gonna stay in here. I'll lock up when I'm done.
Sounds good.
That's where I get most of my work.
So the questions are pretty good, they're pretty specific, but in terms of like the running shoe, it could be any running shoe?
Anyway, yeah, so I'm
Okay.
talking about just running shoes just in
In
general.
general, okay. Yeah, 'cause
If you want to study a specific one, I think that's a good idea too, because then you can talk more details of what they specifically did, like Nike or Adidas or something like that.
Okay, cool.
But what I had in mind was just in general,
In general, okay.
but a specific one would be fine.
Because I know they have like the spike ones, and they got like the
Yes,
jogging ones.
That's true. That's true. Yeah, either one of those I think would be.
Okay, cool. Thanks.
The exam was just, if anything, I think it was a little too easy.
Yeah.
But yeah, I had seen a lot of that stuff in my previous differentials of linear algebra class, so that was like just
I just banged it out. I hardly even had to study or anything. And then now compared to this semester, it's like.
Sanjana, do you have any more questions before I close up the Zoom call?
Yeah.
Okay, so I'm gonna close up. So if you have any more questions, just email. Okay.